In my third session, I am going to discuss a special problem based upon which you are going to solve question number 14 by yourself. Okay, because I can see that question number 14 contains 5 tuples. Okay, so 5 tuples means in this ordered pair 5 items are there. Okay, so I have to deal with long elements. So therefore I have chosen a similar type of problem, and I'm going to show you the methodology to deal with this sort of problem. This methodology will be applicable to problem number 14. Okay, so the question I'm writing, this question is not with you. So question I'm giving, first of all, let me give you the question. It is find a basis okay, the question is find a basis and dimension of the subspace W of R3, where W is given as a set of all such points belonging to R3 which satisfies the equation this. Carefully observe this particular problem. It's a very important problem, so carefully observe. This problem may look very similar to problem number 13, but there in certain part of the logic, there is something which is different from the previous example. Okay, you will get to see it. So let us select a point. So let us denote this point by, you know, this term, it is called xi. This name of this particular term is called xi. It is a Greek letter, alpha, like alpha, beta, gamma. So this let us name a vector xi by the triplet point ABC, which is belonging to this particular set W. Okay, what is the first difference? The first difference of this problem to the earlier one is that the system was given, and from that system we found the solution space, and that solution space was actually the subspace. Now the system is not given, but subspace is given. In subspace, the triplet is satisfying a condition. This condition is given over here. So I'm going to find a basis for this particular subspace, because every subspace is a vector space and every vector space has a basis. So I'm going to find a subspace, and I'm going to count how many elements are there in this subspace, in this basis, and that count will be reflecting the dimension of that subspace. Okay, the dimension of R3 is equal to 3. That doesn't mean the dimension of any subset of R3 will be 3. Okay, let us find it out by ourselves. So xi equal to ABC, that is an arbitrary point from this particular set. And so since the point has been selected from this particular set W, it satisfies the condition given in W. So A plus B plus C equal to 0. A plus B plus C equal to 0. And here also we see that there are 3 variables. There are 3 variables and 1 equation. There are 3 variables and 1 equation. And so 3 minus 1, that is 2 variables have, or maybe chosen independently without any loss of generality, without any loss of generality. let us call these independent vectors by B and C. Okay, you could have chosen A and B, or you could have chosen A and C, but since we are that thing is not important. Which pair will be chosen as independent? Important is how many will be independent. So the answer is two. Two variables will be having independent chains, and therefore, if we talk about this equation A plus B plus C equal to 0, and if these two variables are chosen independent, that means this implies that A can be expressed as minus B plus C. A can be expressed as a linear combination of these two. Okay, and therefore the vector xi takes the form A comma B comma minus A plus B. That is your vector. Okay, now carefully observe one important thing. I am going to extract out the skeleton out of this vector, because this vector is not in its actual form. This vector is, you can see that this particular term, just a minute, is C equal to, oh, okay, so let us write it as okay, let us do one thing. Let us consider A and B to be our independent vectors, not B and C. You can do it by B and C also. Let us do it by, because actually when I solved this particular problem in my copy, so I actually considered A and B to be independent. Okay, so therefore let us choose this A and B to be independent. A few changes let me make, very simple changes. So by vectors by A and B. Okay, and in this scenario, in this case, we can write this vector C in terms of minus A plus B. Okay, now you can justify why have I written A B comma minus A plus B. Okay, because before, see, this particular problems actually requires much thinking. So before coming to the class, I scan the exercise, I select a few problems, I solve these problems by myself, and once I'm satisfied that this problem can be discussed and it has a relevance, then these problems are chosen and it is discussed. If I select an arbitrary problem right now, then it may kill some time, because this particular set of problems requires much thinking. Okay, definitely if you are stuck with a particular problem and if you need my help, you have to tell me in advance so that I can get sufficient amount of time to think over it. Okay, because the solution of this exercise is not available to me. Every day before coming to the classroom, I select a few problems and I solve it by myself, and I try to discuss those problems in the class. Okay, now you see, if you want to extract out, if you want to by seeing this element, you see that this element is the sum of the first two elements. So obviously this vector is the sum of two different vectors. So what I can do, I can separate the two vectors in a following manner, and this step is very important. This step which I'm going to do is very important step I'm going to show, and this has no universality. It will vary from problem to problem. You will acquire a kind of efficiency, and by looking at this sort of problem, you'll be able to understand how to separate them. So let us do it. I think you will not be having any trouble if I write the particular first vector in terms of A only, and the second vector in terms of B only. I hope that you will not be having any problem in understanding that. Okay, I'm separating A and B. This is your A part and that is your B part. Okay, and you see, if I take common A, I can write it as 1, 0, minus 1, and B, if I take it common, so we can write it as 0, 1, minus 1. Okay, so you see, what from this particular thing, what we have come to see is that xi, the vector xi is expressed. The vector xi is expressed as a linear combination, of vectors, 1, 0, minus 1, and 0, 1, minus 1, and 0, 1, minus 1. So this means that this xi vector is actually belonging to the span of the set containing these two vectors. I hope you understand what I mean. The span of these two vectors. Okay. Now we selected xi from where? We selected xi from W, and that is xi belongs to W, and we have shown that this implies the option, because there is a sort of network connection from my end, I hope. And if I think that I have lost my previous board work, is not a big issue. I can continue from here. So what I got is that xi was actually belonging to W, and we have shown that xi now belongs to the span of the set containing the points 1, 0, minus 1 and 0, 1, minus 1. So that means what? That means, and since xi is arbitrary, just a minute. Since xi is arbitrary, so W is actually becoming subset of this set. W is actually becoming subset of this set. Why is it so? Why? It is because if I show that X belongs to A implies X belongs to B, this implies A subset of B from set theory. So W is a subset of this by our mathematics. Again, L 1, 0, minus 1, 0, 1, minus 1, this set, this span, linear span of this set, this is what? This is actually all possible linear combinations of the vectors given over here, all possible linear combinations of the vectors given over here. That is the set under consideration. So this set is actually subset of W. This set is actually subset of W. Why? Try to recall a result which I discussed. If V is a vector space, and W is a subset subspace of V, then or let us denote this by not by W, by S, or okay, W is a subspace of B, and then S is a subset of W, so that linear span of S is actually W, then LS is actually contained in W, and W is contained in V. So LS is actually the smallest subspace contained in V. LS is a subspace that can also be shown. All these examples are there in the previous chapters. Okay. So therefore, LS is the smallest subspace of W. So if I consider this to be my equation 1 and this to be my equation 2, so from 1 and 2 we get W is equal to 1 0 minus 1 0 1 minus 1. Why? Because A subset of B and B subset of A together implies A equal to B, and that implies the set 1 0 minus 1 0 1 minus 1 generates W. Okay, first part is done. Now the second part is also very interesting. In the second part, next we want to show that the set 1 0 minus 1 0 1 minus 1 is Li. Now how can I show it? Okay, I'm going to stop the current share. I'm going to stop the current share and I'm going to show you a result which is there in your book. Okay, first of all, this result is let me find the result first of all. It is in the previous chapter. Probably you are seeing what I'm showing to you. I have to find it out before I say something about it. Yeah, in this chapter. So this result is there in the problem, in the exercise. So if anybody tries to solve the exercise, he will get to see the result, otherwise not. So I'm showing you which result I'm talking about. Okay. See this result. Let U and V be distinct vectors. I hope you have solved it. Let U and V be distinct vectors in a vector space V. Show that let U and V be distinct vectors in a vector space V. Show that UV is linearly dependent. The set UV is linearly dependent if and only if one is multiple of the other. If UV is linearly dependent if one is multiple of the other. Now you see this result is there as an exercise in problem number 9 of the previous section, that is section 1.5. Section 1.5. So I'm going to use this result to the current problem. So let me show you how. So now to show that this is Li, actually what is the definition of Li? The definition of Li is that two vectors W1 and W2 is Li if there exist scalars A1 and A2 such that when zero vector is expressed as linear combination of these two vectors, only possibility is that these vectors are individually zero. Then it is Li. Now, what is the result that I showed you? This result says that if we have two vectors, the result is showing that if you have two vectors u and v, and these two vectors are distinct, then uv is linearly dependent set if either u is some multiple m1 of v, m1 belonging to the field, or v is some multiple of u, where m2 is belonging to f also. Okay, that result is given over here in problem number 9. In problem 9. Okay, so you see, I don't have to use this particular definition to show that this set is Li. I'm going to show it. Okay, you see, we see from above that the vector 1 0 minus 1 is actually is not a multiple of 0 1 minus 1, because this term, the middle term is 0 over here and this first term is 0. You cannot express this as a multiple of this. Neither 0 1 minus 1 is multiple of 1 0 minus 1. None of these is multiple of the other, and therefore by this rule these vectors 1 0 minus 1 and 0 1 minus 1 are linearly independent. That means the set containing these vectors, is linearly independent. Therefore, this set spans V. Point number 1 is that 1 0 minus 1 and 0 1 minus 1 spans W, and this set 1 0 minus 1 0 1 minus 1 is Li, and therefore 1 0 minus 1 0 1 minus 1, let me write it in another page because it's a very important result and it's very important also. Just a minute. So we have seen that the set 1 0 minus 1 0 1 minus 1 is a basis of W, is a basis of W. Now, how many elements? The number of elements present, the number of element present, I can name this basis as B. In B is 2, and so dimension of W is equal to 2. This result is very important in the sense that, is carefully observed, W was a subset of R3. W was a subset of R3, and we know that basis of R3 contains how many elements? 3 elements. three elements for which we say that dimension of R3 is equal to 3, but there may exist a subset, or rather subspace to be more general, of R3 whose basis may contain elements lesser than the number of elements present in R3, in basis of R3. So if a vector space is there, and if it has a finite basis, if the vector space has a finite basis, okay, and it has a dimension, then a subspace of that vector space will have a finite basis whose dimension may be not equal to the dimension of V. So the question is what is the connection between, if V is a vector space and W is a subspace, question is what is the connection between dimension of W and dimension of V? What is the connection between these two? This is an example which I have shown. What is the connection between these two? And you will get to see, let me stop presenting this particular board work. I'm done with the board work. Let me show you the book once more, and let me show you, see by the result by yourself. Okay, that I actually mean to say. So you see, theorem 1.11. Let W be a subspace of a finite dimensional vector space V, then W is finite dimensional, and dimension of W may be lesser than or equal to dimension of V, may be less than dimension of V, or sometimes dimension of W is same as dimension of V. Moreover, if dimension of W and dimension of V are same, then V equals to W. Okay, if the two dimensions become same, then actually there is no difference between V and its subspace. Okay, every vector space is a subspace of itself. So therefore, then in that case, it will be like this. But otherwise, if W is a non-trivial subspace of the vector space, its dimension will be always lesser than this. This is a very important result. Okay, and many such important results are there in this particular chapter. So you have to go through them, and you have to, not only this, you have to memorize them too. This is a very important diagram. Probably you have seen it and probably you have thought over it. This is an overview of dimension and basis. So you have, on one side you have a linear independent set. Okay, this portion, all these vectors present over here are linearly independent vectors. All these vectors generate the vector space. The universal set over here is the vector space. Okay, so if I combine them together, if the linearly independent set, if I consider those vectors which can generate the vector space and they are linearly independent, then that set is termed as, that intersection is called basis. Or if I consider those linearly independent vectors which can generate the vector space, they become basis. So this result is very important. Okay, and similarly we have some other results over here. One result I want to read it out for you. It is in the corollary section. This result states that let V be a vector space with dimension n any finite generating set for V contains at least n vectors. Okay, and generating set of V that contains exactly n vectors is a basis for V. So if we can show that, you don't have to show that the vectors are linearly independent at all. If we know that vector space, suppose I am saying that, okay, this is a vector space and it has got this dimension. Okay, and if you can find out a generating set which generates the vector option, I'm almost done with my today's class. So what I wanted to say, wanted to say to you, time is also running out, that if you know that a particular vector space has some sort of dimension, and that dimension, and if you can find, with this knowledge, if you can find this generating set which generate that vector space whose dimension is known to you, automatically you can say that that generating set is obviously a basis. You don't have to prove that the generating set is alive. If you know the dimension, if the dimension is not known, then you have to show both of this. Or if you can find any if I say that this particular vector space has dimension this n, now if you can find a linearly independent set which contains n vectors, you'll automatically understand that it is a basis. Okay, but for both of these scenarios, you have to know what is the dimension of the vector space I'm talking about. And the last one is that every linearly independent subset can be extended to a basis. If you have a linearly independent subset, you can extend that, you can add elements to that, and you can make it a basis. Okay, so with this, I'm going to end my today's session. Thanks for your patient hearing, and I hope I am able to communicate the problems which were tremendously important I could communicate to you. So you are supposed to solve the other problems of this particular chapter, and if you do so, you'll be benefited. Someone has raised his hand. If you want to say something, you quickly say, because time is running out. You can unmute yourself. I'm done with my class and you can ask me. I'm going to end my today's session. We are going to meet again on Thursday morning. Bye.